we're rejecting the null hypothesis for the wrong reason. Suppose that your null hypothesis is that theta is greater than 0 against the alternate that theta is less than or equal to 0. It should be the other way. So this is a one-sided test. People construct one-sided tests all the time. But Hone wanted to see a one-sided test instead. So when would we reject the null hypothesis? Well, we would reject the null hypothesis when we see, for this statement of the null and the alternate, a t-statistic that's a large negative number, a very small number on the real line. Okay? That is to say, a t-statistic is much different from 0. We don't reject the null when the t-statistic is close to 0. A little more, let's go back to that two-sided test. Oh, incidentally, can you construct one-sided confidence intervals? Sure. A one-sided confidence interval might be from minus infinity to an upper bound, or from a lower bound up to plus infinity. When I was a graduate student, I taught in the basic statistics sequence at the University of Illinois, and we always put that question on the term or the final to find out which kids were really tuned in. We have a regular two-sided confidence interval, and then we always throw on a one-sided confidence interval to see who's really been paying attention. So in this case, we reject the null for extreme t-statistics, really big or really small. But if they're close to 0, we can't reject the null. Okay, so don't forget that. So we're always looking to see whether or not our test statistic, whether it's f chi-square t, is an extreme observation, extremely different from 0. If it's close to 0, you shrug your shoulders and you say, I can't reject the null. Oh yeah, serial correlation I want to talk about. We talked last week about heteroscedasticity. Let's talk about autocorrelation. So we talked about heteroscedasticity before the Thanksgiving break. We talked about heteroscedasticity, which is a cross-section and a pathological disease of cross-sections. What we want to talk about tonight briefly is serial correlation. If I observe one of you over the course of time, then a disturbance that perturbs your behavior today is probably going to continue to have some impact on you tomorrow. So we're living through that right now, right? The gyrations in the stock market. Shocks to your decision-making last week are still echoing through the decisions that you're trying to make this week. So that the shocks or the errors that happened in the past are still having an impact on us today. So the idea is that we start with a garden variety regression model, y is equal to x beta plus u. But now, instead of the error term being independent across periods, we say that today's disturbance depends on a realization of the white noise term today, as well as what happened yesterday, some fraction of what happened yesterday. So that UT, today's disturbance, is a fraction of what the disturbance was yesterday, plus the white noise term, epsilon t. What's white noise, by the way? Elevator music. What's elevator music? Really boring, monochromatic music that you hear in the elevator, okay, because it's completely inoffensive. Okay, so, or when you turn on your solid-state hi-fi system, there's a little hiss in the background. These days with iPods and things like that, I guess you don't get that stuff. You have that noise in. Oh, yeah. White noise would be the. I guess I've been here too long, I don't even hear it anymore. White noise would be the air conditioner noise that you hear in the background. It's sort of a constant level of noise. There's a little bit, if you listen carefully, there's a little bit of variation as the wind blows across the building, that kind of thing. So the variance in the noise level is very small, and the mean level of noise is constant, so that's white noise. So that the error term today is a fraction of what happened yesterday plus today's white noise term. The white noise term is independent from period to period, so that the expected value of epsilon s times epsilon t is sigma squared epsilon if t and s match, and is equal to 0 if the t and the s don't match. And beyond that, we assume that the fraction of the error last period that's carried forward to this period is a number between -1 and +1, strictly greater than -1, strictly less than +1. Why do we do that? Why do we have to impose that restriction on rho? Yeah. Why do we have that restriction on rho? What's Ben Bernanke hoping about the financial system? Is he hoping that there's an inherent stability? There's an inherent stationarity, that what we're going through is just a deviation from the long run, so we will return to some kind of steady state growth? Well, suppose that rho was bigger than 1. That would mean that what the error last period was carried forward to this figure and was even bigger. And so the errors would be accumulating with the passage of time, and the model would explode. It would produce wild swings. So we impose the restriction that rho be between -1 and +1 for purposes of stationarity. What? Rho propaganda. Propagation. All right. So we want to. The errors are propagated, but they're diminishing with time. If rho was 0, there wouldn't be any propagation. We want a little bit of propagation, but not too much. We want to have a little bit of inertia from period to period, but not too much. So one of the things that we need to do is, because again, we're in the business of testing hypotheses, so we need to know whether or not this pathological disease of serial correlation has an impact on the unbiasedness of our estimator, whether or not it has an impact on the consistency of our estimator, whether or not it is going to have an impact on the efficiency of our estimator. If these properties are not what squared is unbiased, whether or not it's consistent, whether or not it's efficient, we need to be able to test for the presence of serial correlation, and we need to know what the same propositions held for our consideration of skedasticity. We wanted to know if whether or not a deviation from scalar diagonal error covariance matrix resulted in bias, inexistent estimators, or inefficient estimators, how do we test for it, how do we correct for it, and so forth. So the same thing. No. Just to make sure that the error process doesn't explode. So that's our again. Unbiasedness, consistency, efficiency, testing for the disease, correcting for the disease. So a good place to start would be to construct the exact error covariance matrix. Another time period. S and T is different. So if S is equal to T, then the expected value of epsilon S and epsilon T. There's no covariance between times. To start constructing the error covariance matrix, what we're going to do is substitute away from ut minus 1. Ut minus 1 must be equal to epsilon t minus 1 plus some fraction of error that happens the period before that. So we'll substitute in the ut, and so we can see that today's disturbance depends on today's white noise and the white noise that occurred last period and the disturbance 2 periods ago. So if we continue to substitute away from the u's, we get metric series of the white noise. And the first thing we need to worry about is whether or not this complicated error structure that we've specified has a 0 mean. Remember, our garden variety assumption was that the expected value of the error term was 0. So now we have a very special construct for our error term. We've got to check and make sure that the disturbance term still has a mean of 0. So since it's just a weighted average of the entire history of the white noise, and each white noise term has a mean of 0, our new error term still has a mean of 0.